Hi, and welcome to the video. In this video, we're going to be discussing the annihilator approach to solving differential equations. So, before we can go too far into the method, we need to talk about what's going on here. So, when we go to solve a non-homogeneous linear differential equation, we have to find the complementary solution and the particular solution. Remember, the complementary solution goes with solving our one side that's got our functions of y, y prime, y double prime, on out to the nth derivative of y is equal to 0. And then the particular solution is solving what's going on the other side. So if I've got f of y, y prime, y double prime, on out to the nth derivative of y is equal to some g of x, that particular solution goes with the g of x portion. Now, this annihilator approach that we're about to discuss works great whenever you have constant coefficients, and it works well whenever you have g of x that's a finite sum or product, so no quotients, but sums or products of constant functions, polynomials, exponentials, sines or cosines. So again, what does that leave off the table? Well, it's not going to work well for logarithms. It's not going to work well for tangents and secants. It's not going to work well for cosecants and cotangents. It's not going to work well for anything that is a rational function with a denominator, anything that is an inverse trig function. So we have well-behaved functions that work well with this approach, and that's what we really have to focus on when using the annihilator approach. To use the annihilator approach, we first need to talk about what is called the differential operator. So we can denote a derivative with this capital D to an n power that denotes the nth derivative of whatever it's applied to. So d to the n of y is the nth derivative of y with respect to x. That's what we're denoting with this. It's just kind of a shorthand. You should have seen this in Calc 1 as an alternate kind of notation. It doesn't get used a whole lot until we get here to differential equations. So if we were going to rewrite this dE, that is a sub 3 y triple prime plus a sub 2 y double prime plus a sub 1 y prime plus a naught y is equal to g of x, with the differential operator, what it would look like is a sub 3, and let me clean up that 3, a sub 3 d cubed of y plus a sub 2 d squared y plus a sub 1 dy plus a naught y is equal to g of x. And here's a wild thing that we can do with the differential operator. We have y involved in every term, and we can say that the operation that's being done with y here is this full picture that is a sub 3 times the third derivative of y plus a sub 2 d squared plus a sub 1 d plus a naught. And all of this is applied to y, right? So that's kind of the wild thing that we can do with the differential operator, is that it is an operator. It is working on y. It is creating a derivative, but we can use this notation to kind of pull it out and treat it like we can factor things and that sort of idea. So when we talk about an annihilator operator, that's a differential operator that annihilates or turns to 0 a given function. So if I think about what does it take to annihilate a constant, well, I just need a single derivative to create 0. If I'm going to annihilate x, I need two derivatives to get rid of a singleton x, right? If I'm going to get rid of x squared, I need three derivatives, right? Because the first derivative is 2x, second derivative is 2. I'm still not at 0, so I need that third derivative to give me 0. So that's what we mean by an annihilator operator. Now we'll get more into that in just a moment, but let's write this differential equation with the operator notation. So I'm going to write y double prime as d squared y, and that's a minus 5. Y is equal to x cubed minus 3x. And really, we've got it in the differential operator notation there. But we could go ahead and pull out the y to make this d squared minus 5 by y is equal to x cubed minus 3x. And that would be operator notation for that dE. In a similar way, we can look this one and see that I can rewrite this as d cubed y plus 4 dy is equal to e to the x sine of x. And I can pull out the y to give me that this is d cubed plus 4d by y that is equal to e to the x sine of x. And really, I could treat that thing as d by d squared plus 4 by y. That's equal to e to the x sine of x. And that would be a simplified operator notation for my dE in that case. Now, we mentioned just a moment ago that an annihilator is something that brings something to 0, right? How many derivatives does it take to bring something to 0? And does it take a little bit more than just a derivative to make something 0? Well, with polynomials, we see that it's just one more derivative than the degree of the polynomial, right? The highest exponent. You just need one higher derivative to make it happen. Now, when it comes to e to a power, well, let's think about this. If I had e to the 3x, its derivative is going to be 3 e to 3x. Well, if I took the derivative of e to the 3x and subtracted 3 e to the 3x, that would be 0, right? And that's why we have this derivative minus alpha for the case of something that has e to the alpha x. Now, if we have any kind of x as a product with that, well, then we have to raise this to the power, because as you start taking derivatives, you have the product rule going on, and that kind of changes the dynamic. Now, if we've got something that's got sines and cosines, well, think about the second derivative of sine. That is a negative sine, right? Two derivatives gets me there. Two derivatives of cosine gets me negative cosine. So that's where I get the d squared plus b squared. Because if I had sine of 3x, it would be a negative 9 sine of x. 3x. Negative 9 sine of 3x. Right? So that's how that would play out for us. That's why we need d squared plus b squared to change it out. Now, if we get a combination of all this, well, if I have e to the ax by cosine or x e to the ax by cosine, well, there's the d minus a to take care of the exponential. That thing is squared and added to beta squared to help me with the cosine or sine portion. And then it's raised to the n to help me with the polynomial portion. So you see how these different annihilators come together. Why are we talking about an annihilator? Well, at this point, we know how to solve a homogeneous dE, where you have 0 on the other side. And now what we're seeing is we can use these annihilators to create 0 on the right-hand side, even when we have some sort of non-homogeneous portion where you have something other than 0 over there. We use an annihilator, we get rid of what's on the right-hand side, it's now 0, and we know how to shine with this kind of situation. So let's just think about for a moment annihilating these different expressions. So with this pure polynomial in the first one, all I would need is d to the fifth. 5 derivatives will get rid of everything in that expression. In the second one here, I'm going to need something that looks like d plus 4. For the third one, I'm going to need, first off, I would need the d minus 3, but because I have x e to the 3x, I'm going to go ahead and do it squared to get rid of this portion. All of that automatically gets rid of this, but now I need the square to take care of my x. Now, with the sine of 4x, what I've got is that I need d squared plus 16 to annihilate it. When I get into the territory of having x cosine of 2x, I've got d squared plus 4 squared. And then when it comes to x e to the 3x plus sine of 2x, what I'm going to need is that d minus 3 squared plus 4 for the coefficient on x within sine, and then this is squared to take care of that x right there. So that's how we annihilate, right? Because in this last one, once again, I have alpha is 3, beta is 2, and n minus 1 is 1, meaning that n is 2. So that's how we annihilate. Now let's verify that a proposed annihilator does indeed annihilate an expression. So let's take a moment to look at what goes on with d squared plus 9 with 2 cosine of 3x minus 7 cosine of 3x. If I think about the derivatives of cosine of 3x, so let's just go there. First derivative of my 2 cosine of 3x is a negative 6 sine of 3x. That means that my second derivative of 2 cosine of 3x, which is just the derivative of that thing, is going to be a negative 18 cosine of 3x. Then if I look at the sine portion, the first derivative of my minus 7 sine of 3x is going to be a negative 21 cosine of 3x. And my second derivative is going to be, let me get it written here. Once again, it's just the derivative of that, so it becomes a positive 63 sine of 3x. So all of that together means that the d squared plus 9 applied to 2 cosine of 3x minus 7 sine of 3x is going to play out as my second derivative of that whole expression plus 9 times that expression as well. So as we just saw, I have a negative 18 cosine of 3x plus 63 sine of 3x plus, now I bring through the 9, and I've got 18 cosine of 3x minus 63 sine of 3x. Well, those are opposite signs, and I have 0. Just like I expected to have with this annihilator. So how do you solve differential equations with annihilators? The first thing you're going to do is find the differential operator that annihilates the non-homogeneous portion g of x. You're going to find the complementary solution for the associated homogeneous equation. You're going to find the general solution for the non-homogeneous equation. You'll separate y into the complementary solution and the particular solution. You're going to line up that particular solution within the original framework, right? So you'll take its derivatives, put it into the original, and line up the coefficients to see what is equal to what. Then you go back to combining your complementary solution with your particular solution for the general solution. What does this look like in practice? Well, let's take a look at an example. Actually, I believe I have 3. So let's start with the complementary solution. So that complementary solution comes from having y triple prime plus 2y double prime plus y prime is equal to 0. Now, we can use the auxiliary equation. Y is equal to e to the mx. That gives us m cubed plus 2m squared plus m is equal to 0. So m by m plus 1 squared is equal to 0. When I factor that down, I have a repeated root, which means that I have to do reduction of order with it. That gives me m is 0 and m is negative 1 with that repeated. So my complementary solution ends up looking like c sub 1 e to the 0x plus c sub 2 e to the minus x plus c sub 3 x e to the minus x. And that is to say that I have the complementary solution is c sub 1 plus c sub 2 e to the minus x plus c sub 3 x e to the minus x. So we've done the easy part. Now let's look at finding the particular solution. How we're going to go about doing that is let's translate this into differential operators. So we've got d cubed y plus 2 d squared y plus dy is equal to 10. How do you break that down? Well, I can pull out a y, and this thing will factor much like my auxiliary equation did. I'll have d by d plus 1 squared by y is equal to 10. Now, how do you annihilate 10, right? Let me go ahead and move this 10. Well, if I can get the whole thing moved. So I've got this 10, and I'm going to go and apply another differential operator to work to annihilate the 10. So with that, I have d squared by d plus 1 squared y is equal to 0. Translating this into an auxiliary, we end up with something that looks like m squared by m plus 1 squared is equal to 0. The only difference between this and what we had up here is now that m is repeated. So what does that mean? Well, for our particular solution, the only difference is we have a c sub 4 x e to the 0x, or just c sub 4 x. That is our particular solution. But we're not done. We can work with a particular solution to get the coefficient of the particular solution solved. So if I think about derivatives here, so my first derivative would be just c sub 4. My second derivative of my particular solution would be 0. My third derivative of my particular solution is also 0. I go back to my original. I have that it's y triple prime, so 0, plus 2y double prime, so 0, plus y prime, which is c sub 4, and it's equal to 10. That means that c sub 4 is 10. What in the world does this mean for the solution in general? Well, our general solution is y is equal to the complementary solution, which was c sub 1 plus c sub 2 e to the minus x plus c sub 3 x e to the minus x plus our particular solution, which was 10x. So again, this portion here is the complementary. This is the particular. It's particular because it is solved to go particularly with that non-homogeneous portion. That's why it's the part that can have a known coefficient. Let's move on to another example. Here we have something a little more complicated on the right-hand side, but we'll get into that. Let's first deal with our complementary solution. So working with complementary, we have that if I use y is equal to e to the mx, then I've got m squared plus 4 is equal to 0, right? Because we do y double prime plus 4y is equal to 0 for the complementary. That means that m is plus or minus 2i. Now you'll notice that that is a 0 for alpha and 2 for beta in the formula that we had previously with auxiliary equations. If you had the complex roots, we said that if I have alpha plus or minus beta by I, that translates into e to the alpha x by c sub 1 cosine of beta x plus c sub 2 sine of beta x. So in this case, my complementary solution is just c sub 1 cosine of 2x plus c sub 2 sine of 2x because I have e to the 0th out front, which is just 1. Looking at my particular solution, what does it take to annihilate this? Well, let's put this in annihilator form to start with. What we need is a combination of just one derivative to take care of the constant term, and then I need a d squared plus 1 to take care of, well, it's just x inside of sine and cosine there. And then we have the leftover d squared plus 4 from previously. And now that's annihilated. Move into the auxiliary equation that goes with this. I've got m by m squared plus 1 by m squared plus 4 is equal to 0. So I get additional solutions of m is 0 and m is plus or minus I. Again, we already dealt with that with our complementary solution. So in our particular solution, to this point, we have that it's equal to c sub 3 plus c sub 4 cosine of x plus c sub 5 sine of x. Now, if I look at the first derivative of that, I've got a minus c sub 4 sine of x plus c sub 5 cosine of x. If I can look at my second derivative, I've got a minus c sub 4 cosine of x plus, or actually minus c sub 5 sine of x. Let's put this into the original, which gives me a minus c sub 4 cosine of x minus c sub 5 sine of x plus 4 c sub 4 cosine of x plus 4 c sub 5 sine of x is equal to, oh, I almost left off that additional term, that is plus 4 c sub 3. And that's going to be equal to 4 cosine of x plus 3 sine of x minus 8. Now, let's think through this. We've got 3 c sub 4 cosine of x plus 3 c sub 4. Let me get my red back. C sub 4 sine of x plus 4 c sub 3 is equal to the 4 cosine of x plus 3 sine of x minus 8. Let's just point some stuff out. Cosine and cosine, those coefficients should match up. So I get that 3c sub 4 is equal to 4. That means that c sub 4 is, I'm sorry, I've got a c sub 4 right there. That should be a c sub 5. Okay. Keeping that up. C sub 4 is going to be 4/3. Then I look through here. I've got 3c sub 5 and 3 sine of x and 3 sine of x. So 3c sub 5 is equal to 3. So c sub 5 is 1. Finally, I've got 4c sub 3 is equal to negative 8. So c sub 3 is negative 2. In the end, what does that give me? That gives me, and let me make sure that I've got all my pieces here, that y is equal to c sub 1 cosine of 2x plus c sub 2 sine of 2x minus 2 plus 4/3 of cosine of x plus sine of x. Again, complementary and particular. Let's do one final example where we won't have any unknown coefficients left in the final answer because we have initial conditions. All right, so let's just run through the process. This might take a little bit longer because we have initial conditions, but we work it much the same. So let's see it out. Again, let's go to the complementary solution. That means that we're setting y double prime plus 5y prime minus 6y equal to 0. And we're using y is equal to e to the mx to help us out with this because we have constant coefficients. With this, we end up with the auxiliary equation that looks like m squared plus 5m minus 6 is equal to 0. That thing factors as m minus 1 times m plus 6, 0. So m is 1 and m is negative 6. My complementary solution looks like c sub 1 e to the x plus c sub 2 e to the minus x, 6x. Looking at what I have here to try to address my particular solution, let's write it with the differential operators. I've got d squared y plus 5dy plus minus 6y is equal to 10e to the 2x. That means that I have d minus 1 by d plus 6 y is equal to 10e to the 2x. What does it take to annihilate e to the 2x? Well, it takes d minus 2. Now, looking at this, if we translate this again into an auxiliary equation, we've got m minus 2 by m minus 1 by m plus 6. Because these two were already covered in the complementary, we don't have to worry about them again. That would be repetitive. There's no need to be repetitive. We have m is 2 is the only solution that we get for the particular solution. So at this point, we can say that y is looking like c sub 1 e to the x plus c sub 2 e to the minus 6x plus c sub 3 e to the minus 2x. If I look at my particular solution and its derivatives, I've got 2e to the 2x for its first derivative, and its second derivative is 4e to the 2x. If I go back to my original and put that in, I've got 4e to the 2x plus 10e to the 2x minus 6e to the 2x. I'm sorry, I've dropped off my c sub 3 that goes with that. So it's 2c sub 3, 4c sub 3. Let's fix this. We can't forget the c's, so don't fall prey to the same thing that I just did, c sub 3. So I've got, let's start this over. 4c sub 3 e to the 2x plus 10 c sub 3 e to the 2x, right? I've got 5 by the 2 to give me the 10. Minus c sub 3, or 6 c sub 3 e to the 2x is equal to 10 e to the 2x. Well, what does this yield? Let me double check my numbers here. So I've got 4 plus 10 minus 6, that should be 8. E to the 2x is equal to 8 c sub 3, e to the 2x is equal to 10 e to the 2x. Well, I hope that you can see that c sub 3 is 5/4. Now let's use the fact that y of 0 is 1 and y prime of 0 is 1. If I go back to my original, right now what I know is I have y is equal to c sub 1 e to the x plus c sub 2 e to the minus 6x plus 5/4 of e to the 2x. Y prime is equal to c sub 1 e to the x minus 6 c sub 2 e to the minus 6x plus 5/2 of e to the 2x. Okay, let's work with these two. If I put in x equals 0, I get that y is equal to c sub 1 plus c sub 2 plus, actually, it's not just y. Y was equal to 1, so it's 1 is equal to c sub 1 plus c sub 2 plus 5/4. And that means that c sub 1 plus c sub 2 is a negative 1/4. If I go to put in x is 0 into the first derivative, I get 1 back, and I've got c sub 1 minus 6 c sub 2 plus 5/2. That means that c sub 1 minus 6 c sub 2 is equal to a negative 3/2. Now, if I just add, let's subtract these two out, actually. Right? If I subtract these two equations from each other, I end up with 7 c sub 2 is equal to, well, 1/4 plus that 3/2 is going to leave me with 5/4. So c sub 2 is going to be a weird number. It's 5/28. Now, I can go back to the first one, put that in. I've got c sub 1 plus 5/28 is equal to negative 1/4. That means that c sub 1 is going to be, well, let's just double check this. Multiply that by 7. I've got 7/28 minus 5/28 gives me negative 12/28. That's a negative 3/7 whenever I reduce the factor of 4 out. What does this mean? I know that my solution at this point is a negative 3/7 of e to the x minus, or plus 5/28 of e to the minus 6x plus, where did it go? 5/4 of e to the 2x. That is my exact solution for this particular DE with these initial conditions. So I can solve for all three coefficients with those two additional pieces of information. So this is our method. This is the Annihilator approach. It's very handy for these non-homogeneous DEs with well-behaved right-hand sides. So we'll talk more about more methods coming up, and I'll see you then.